Now we shall be dealing with circular motion. In your syllabus you have a uniform circular motion. So let us look into it. What is this uniform circular motion? Now, as the name suggests, you can quite obviously understand that this motion has got to do with a circle. So, if there is a circular path, this is not a perfect circle, but let us just assume this is a perfectly circular path, this being the center of that path. And then, suppose that this distance r is the radius of this circle. And then, there is a particle here. The particle is moving in this direction. So that basically means that it is moving in an anti-clockwise motion. So it's moving in an anti-clockwise direction along this circle, which has got a radius r. Now, what all can we deduce from this particular motion? Well, as long as it is moving in this circular path, it has got a speed. What is the speed? You can find out the speed from your lower class geometry formulas. So the distance it's traveling is the circumference of the circle, which is 2 pi r, and if it is taking a time, say capital T, for moving around this circular path once, then v is the speed with which the particle is moving. Now you see, in this particular formula, 2 and pi are constants, and radius of the circle is also a constant. So if I manage, or if the particle manages to cover this path, to cover the circle once in a same unique time every time, that is to say, if it takes suppose 10 seconds to complete one circle during the first time, and if it manages to maintain this time of 10 seconds for the subsequent motions as well, then the speed of the body is a constant. But even though the speed of the body is constant, the velocity of the body is changing. This particular motion, it has got a uniform speed but a non-uniform velocity. And why does it have a non-uniform velocity? Well, you know that velocity is basically speed that has got a direction. So velocity means displacement divided by the time. So at any instant when we are talking about velocity, we also need to take into consideration what is the direction. Suppose at this point, if I consider this point to be A, the body has the velocity v or the speed v, and it has the direction in this way. Suppose let me draw a standard directions, north, south, west, east. So initially it has a velocity in this direction, that is the southeast direction. Suppose at this point, when the particle has travelled up to this point, it has a velocity towards the north. It is moving towards the north with this same speed. At another point, say at this point, if I call this point B and I call this point C, it's moving along this direction, that is a southwest direction, but it has got the same speed again. So during all points of the travelling, this particle has got the same speed, which is 2 pi r by t. What's changing is its direction of motion. The direction changes from southeast to north to southwest, and at any point the direction is something else. That means though the magnitude of the speed is constant, this is a key word, magnitude, the direction is changing, as a result of which we will say that the body is having a non-uniform velocity. The body is travelling with a non-uniform velocity, though it's travelling with a uniform speed. And how do you find out the direction when a body is travelling in a circle? Whenever a body is travelling in a circular path, then you have to find out the direction at any instant. Suppose I ask you, what is the velocity of the body at this particular instant? In order to find out the velocity, all you need to do is, you need to draw a tangent to the circular path at that point. So if I zoom in on this area, like if this is the circle, and if I ask you what is the velocity at this point, it is basically This is the direction, the tangent. If you know the definition of the tangent as well, but in case you don't know, let me just say that if I draw the radius at that point where I am trying to find out the velocity direction, tangent will be that particular line which will be forming 90 degrees with the radius. That is the tangent. So the tangent that you draw at this surface, keep in mind it will form 90 degree with the radius. You cannot draw some other line like this one or this one. Only that one will be the tangent that forms a 90 degree. So that means that when a particle or any body, it could be you and me as well, if you are traveling in a perfect circular path even with a uniform and constant speed, since we are changing direction at every instant, it is a case of non-uniform velocity, and whenever there is non-uniform velocity, what do we say? The motion is accelerated. It is an accelerated motion. Remember, acceleration did not mean that the body's magnitude of velocity has to change. It's 10, 20, 30 and so on. No. Acceleration might also mean that your magnitude is constant, but your directions are constantly changing. Even that is a kind of acceleration, because even acceleration is a vector quantity. Having said that, well, now you know that when you are moving in a circular path, you are having a accelerated motion. Now, what is the cause of this acceleration? You studied in your class 9 days that force acting on a body of mass m produces an acceleration a. So in order to produce an acceleration, I need this thing, I need a force. So what is the force in this case? Who is providing the force in this case? That particular force is my centripetal force. Centripetal. Petal means towards and centri means center. So centripetal, towards the center. So this is the kind of force. Now what is the cause of this force? So what do we know about this force? Is this a new force? Well, no. Centripetal force is not something different. Other forces act as centripetal force provided what is the situation. So like if I have our sun, and if this is our earth moving round the sun, then there is a force of attraction between the center of earth and the center of sun. What is this force? The force is the force of gravity, given by G mm by r squared. So in the case of a planetary motion, when earth is moving around the sun, or when the moon is moving around the earth, the gravitational force acts as the centripetal force. Centripetal force is not a new kind of force. Other forces manifest themselves as centripetal force based on the situation. If I hold a string with my hand and if I tie a stone to that, and suppose I rotate this stone in a circular path, I tie the string to the end of a stone and I rotate the stone. So in this case, the force between my hand and the string and the stone here is the force of tension in the string. This tensional force manifests itself as centripetal force for this circular motion. You consider the motion of electrons around the nucleus. So if this is the nucleus of an atom, electrons are moving around them according to the Bohr model. Electrons are rapidly moving around the nucleus. So what's the force between a nucleus and an electron? The force between the positive and negative charges is given by the electrostatic forces. Electrostatic. And force electrostatic is 1 by 4 pi epsilon naught charge 1 into charge 2 divided by the distance square. See the remarkable similarity between electrostatic force expression and the gravitational force expression. The 1 by 4 pi epsilon not constant, g is a constant. We have the two charges, we have the two masses. The inverse square of the distance, inverse square of the distance. That's the beauty of this subject. Anyway, so this is Bohr model, and in the Bohr model, the electron is revolving around the nucleus. So in that case, what is the force that's making the electron move around the nucleus? It is the electrostatic force. But here, electrostatic force manifests itself as centripetal force. So the point that I am basically trying to emphasize is that centripetal force is not a new kind of force. Like, it is not something which you can write down in the list of forces apart from force of tension or force of gravity and so on. Basically, these are the different forces, and centripetal force is one of those forces which manifests itself as these forces based on the situation. It's not a new kind of force. The moment you are making a circular motion, the centripetal force comes into play. I can simply hold the this stone with the string like this, not making it move in a circle. Even in this case, the tensional force is present. Otherwise, the string would break and the stone would fall. The moment I make it move in a circle, the centripetal force comes into play. But the tensional force, it's always there, whether you are moving it in a circle or not. So that's the thing. In your book, you will also find something called the centrifugal force. What is the centrifugal force? First of all, let me tell you, centrifugal force is not a real force. It is a fictitious or virtual force. That means it has got no existence in reality. Centrifugal force only exists in the mathematical formulas for our own easy, you can say, in order to solve or ease our difficulties in solving certain problems, we have taken the help of centrifugal force. It is a figment of our imagination. It doesn't exist in reality. Alright, it's a virtual force. So what is the centrifugal force? You have not studied in detail about it till now. Hopefully you will do it in class 11 if you take up science. That there are two kinds of frames of reference. First of all, you need to know that there is something called frames of reference. Frames of reference is like how you view something. So suppose you are going to school by the train or by your bus, and you're sitting by the window and you're looking outside. What do you observe? You see all the trees, you see the buildings, you see the roadside shops whizzing past you, as if they all are moving in the direction opposite to the direction in which your vehicle is moving. That is what you are seeing. But since you know this, you will think that, well, I know the shop or that particular tree or that particular house is stationary in its position. It is because that my vehicle is moving, it's appearing that they are also moving in opposite direction. You know it. But suppose an alien comes from an outside planet who doesn't know about this thing, who does not know that tree cannot move from its own place. And if you make that alien sit into that bus and observe this thing, they will think, oh, the trees are moving, the shops are moving. Alright, you will see everything moving in a direction opposite to you. But imagine someone who is standing on the road. For them, the trees are stationary. For them, you are moving. So we see that the same tree which is moving for one person is at rest for another person. This is the essence of frames of reference. That means whether we see something at rest or whether we see something in motion is completely a debatable topic. It depends upon from which frame of reference you are viewing it. The best example is our earth. Right now, when you are watching this video or I am standing here, it's as if like the earth is at rest. The earth is not moving at all. We can never feel the motion of the earth, do we? We think that the earth is a stationary piece of rock. But ask someone who has seen the earth from outside space. They know how rapidly this earth moves. It's moving at a whopping speed of 30 kilometers per second around the sun. But we never feel it. That's all about the frame of reference. Now this frame of reference can be broadly classified into inertial frames of reference and non-inertial frames of reference. What is inertial, non-inertial? You do not need to know in detail, just know this. Inertial frames of reference are those in which Newton's laws are valid. Non-inertial ones are those in which Newton's laws are not valid. Now, what does this mean? Well, remember this thing, that most of the physics that we study now, that is what you are studying in your class 10, is due to this gentleman. Before the discovery of gravity by Newton, or you have studied about the 3 laws of mechanics given by Newton, you are studying a unit on light. The discovery of whether light is made of 7 colors or not, how do we know this? They were all done by this gentleman. He also has got contributions in the fields of thermodynamics. He single-handedly and independently, apart from another scientist named Leibniz, discovered calculus in order to understand whether planets move around the sun in circles or ellipses. So this person has got a different level of respect in the field of science. Alright, and he maintained this respect right from the 17th century to the 19th century until another genius mind named Einstein came into the picture. Before Einstein, no one dared question Newton, and everyone believed that whatever he said is right. And he said that time is absolute, space is absolute. Those are different things, let's not go into this. So what I am trying to say is, once Einstein came into the picture and started questioning Newton and his ideas, scientists started discovering that yes, even there are certain flaws in Newton's laws. Now what are those flaws? What are those defects? You need not know it right now. You will know it in future if you study physics. But once scientists agreed upon that yes, there are flaws, they found it necessary to make this separation. One frame in which Newton's laws are valid, another frame in which Newton's laws are not valid. Now, since I have already given you a brief idea of the frames of reference, let us discuss this experiment of the merry-go-round that's given in your book. So in your book there is an experiment something like this, that there is a circular metallic platform known by the common name of merry-go-round, where you suppose you, the person A, is standing here, and in front of you there is a tennis ball placed at rest, and then someone started to rotate this merry-go-round, rotating the merry-go-round, and there is another person B somewhere outside watching you. Now we have two observers, observer A, observer B. What is going to happen? Assume that this ball is connected to the center of the platform with a string which is providing a tensional force. That tensional force makes the ball go round in circles, and as I said before, in this case the tensional force will manifest itself as the centripetal force. Now what will the person A observe? For the person A, the ball is at a certain distance, say D, in front of him, and as this thing is rotating, suppose at this point the ball is here, observer A is here, at this point the ball is here, observer A is here. So as the ball is also moving, this person A is also moving because he is also standing on the merry-go-round. So for the observer A, the ball is right in front of him at rest. Now imagine like the entire area outside the merry-go-round is shielded with a metallic plate. You cannot see anything in the outside. And once that happens, when you cannot see anything in the outside, you cannot actually detect whether you are at rest or you are in motion. So during that time, all the observer A is going to see is that the ball is standing in front of him. Just as I gave the example of Earth, me and this camera which is recording this, we are a certain distance apart. And just like the merry-go-round, the Earth is rotating, but we are not feeling it. For us, or for me, the camera is always at a fixed distance in front of me, or it is at rest. So the observer A will say, fine, if the body is at rest, there must be two forces cancelling each other, or this would not be at rest. So observers A said, if this is the ball, Yeah, I agree, there is a force of tension pulling it towards the center, but the ball is not going towards the center, it is right in front of me and all the time. So there must be an outward force in this direction which is cancelling the tension force. So observer A says that must be the centrifugal force. Now for the observer B is simply seeing the ball rotate in a circular path, and he is pretty confident that this is because of the tensional force. The tensional force is providing a centripetal force which is making it go in a circular path. He doesn't even need a centrifugal force for explanation of this phenomenon. Now if at a certain instant of time someone cuts the string from here, what is going to happen? The ball, it will, as I said, in a circular path, they always move along the tangents. So the last velocity that the ball had at this point, with that velocity it will continue moving in this straight line path. So what will B see? B is going to see something like this, moving in circle, 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 straight line. Now B is going to say there was a tensional force which was making the ball go in circles. You have cut the string. Tensional force is absent. It's moving along the tangential path. Matter solved. Simply explained with the tensional force and the centrifugal force. What will be the point of observation from the point of view of A? It will be something like this. A is here, ball is here. After certain time, this platform is still rotating and A is still standing on it. In a second scenario, A will have moved a certain distance in front, say somewhere here, and the ball will be somewhere here, it's moving outwards. In a second scenario, A will have moved even more inwards, and to him the ball will appear to have gone even more far. And then suppose here, now A is here and the ball is here. Finally say A is here and the ball is here. So to A and O, the motion is something like this. A is moving in a path like this, and to him the ball is moving in a path like this. How come is the ball moving away from him? A will say there must be a centrifugal force that's pushing the ball in the outward direction. For his point of view, he will say there's a centrifugal force. And this is where our inertial and non-inertial frames of reference come into existence. What you need to know clearly is B was in an inertial frame of reference, and this person A is a non-inertial frame of reference. How do you know a frame of reference is non-inertial? If any frame of reference is accelerated, it is non-inertial. And this merry-go-round is surely accelerated. It's moving in a circular path, a force is acting on it, so its velocity is changing, so it is accelerated. All kinds of accelerated frames of reference are non-inertial. And so when A was viewing the ball, he was viewing the ball from a non-inertial frame of reference. And in the non-inertial frames, Newton's laws don't hold valid any longer. So this observer A, was not able to explain this motion using Newton's laws. As a result, he took the help of a fictitious and virtual force, the centrifugal force, which helped him explain the motion at last. So centrifugal forces or fictitious forces are those which we need for our own shortcomings in order to describe what's happening in accelerated or non-inertial frames where Newton's law don't hold. There is no such force actually in nature. And let me give one last brief idea that centripetal and centrifugal forces are not like equal and opposite action-reaction forces as you have studied for couples and so on. They are not action-reaction forces.